Are there any questions? Chapter 17.
When it says in this titration is 25 milliliters of 0.2 molar HCl with 0.1 molar NaOH at the half of the sodium point, pH equals pKa, is that true even though the molarity is different? Or does it have to be the same?
The molarities don't have to be the same. Those 0.2 molar what?
HCl
And
0.1 molar NaOH.
it doesn't matter that the molarities are different. The only difference it makes is the volumes. But the points that we have on the curve are still the same. And so here we have a pH. And how many milliliters of HCl? Is that right?
Yeah.
All right, so HCl is twice as concentrated as NaOH. So that means we need twice as much NaOH to reach the equivalence point. And so where's the equivalence point going to come in for this titration? And how many milliliters of NaOH? Well, I neutralize 50. So 50 milliliters of the equivalence point. That's it. So because of the different concentration, otherwise, if they were the same concentration, I'd hit the equivalence point at 25 milliliters rather than 50 milliliters. If they were the same concentration, 25 milliliters of 0.1, and then I'd need 25 milliliters of 0.1 sodium hydroxide to hit the equivalence point. And so the only difference it makes is in the stoichiometry to see where it is. But the features don't change. I mean, the half equivalence point, here the half equivalence point would be at 25. If they were the same concentration, the half equivalence point would have been at 12.5. But the half equivalence point is a half equivalence point regardless of where it occurs in volume. And so the question is about the half equivalence point. The question is not asking where it occurs. If I was asking where it occurs, you'd say 25 milliliters. Now, if the concentrations were the same, you'd say 12.5 milliliters. But the question is not that. The question is about the half equivalence point in general. And so at the half equivalence point, the pH is equal to pKa. Is that true or false? True. 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 False. It's true. It's false. What?
I didn't think I'd learn.
It's false. Why is it false? Because this is where we have HCl and sodium chloride. Is HCl and sodium chloride considered a buffer solution? No, HCl and sodium chloride is not a buffer solution. So HCl and sodium chloride is not considered a buffer. So the pH is not equal to the pKa here. Now, if it were HAC, acetic acid, and acetic acid, sodium acetate and acetic acid, that's a buffer. And so this is not a buffer, not a buffer. We start off with HCl, we start to neutralize it, and we form sodium chloride. Well, sodium chloride is a neutral salt. And so buffer is defined as a weak acid. Well, is HCl a weak acid? No. And a weak base. Now, one thing that tricks people all the time is this. Is this a buffer solution? 0.5 molar HCl with 1.0 molar sodium acetate. A lot of people will say this is not a buffer solution. It's not a buffer because HCl is a strong acid. Is this a buffer solution? Why? This is a buffer solution. Why? Well, technically it's not a buffer solution, but if you were to take HCl and sodium acetate, is HCl and sodium acetate going to exist stably? No, HCl is going to attack the sodium acetate to form what?
Sodium chloride.
Yeah, sodium chloride and
Acetic acid.
acetic acid. What's the limiting reagent? HCl. So we consume all the HCl and we're left with sodium acetate left over and the product, which is
NaCl.
HCl plus sodium acetate yields acetic acid plus water. No, plus salt. Sodium chloride. And so if we consume all our HCl and we don't consume all this, so let's say we have half a molar left, we're going to form half a molar. Do you see that?
Yeah.
And so this was 0.5, this is 1.0, this is 0, this is 0, this goes to completion. So initial change equilibrium. So it's not a buffer, but it's not going to exist. It's going to react and form a buffer. Whereas this is not a buffer and it's not going to react and form a buffer. And so that's a very trick question. But these trick questions you see if you do a lot of problems. If you just do one problem or a few problems, you don't really see the full spectrum of types of problems you might encounter.
So is that graph the titration of the 0.2 molar HCl and the 0.1 molar NaOH? And where did the sodium? Why did that become HCl and sodium chloride?
Oh, that's a product. Let me change this. So HCl and sodium hydroxide forms H2O and NaCl. H2O is a liquid. Let's get into that. And so 0.5, let's say we got 0.5 and 1. HCl is a limiting reagent. We're going to form this. A 0.5 to 0.5 ratio of sodium. Well, actually, no, sorry, I got it backwards. 1.0. We're at the half equivalence point. And so we've neutralized half our acid. So we're left with HCl and sodium chloride. All right, other questions? No? Okay, if there are no other questions, then we're going to continue with chapter 18. I'm going to finish chapter 18 today. In chapter 18, we're learning how to control solubility by doing different things. There are different ways you can control solubility. How can you change the solubility of insoluble?
Change the pH temperature.
Change the pH, change the temperature. pH is discussed in this chapter. Temperature is not. Temperature is discussed in the next chapter, chapter 19. So we aren't going to actually do any calculations with temperature, but temperature will have an impact on it for sure. What else? Change the pH.
Volume.
The volume, you could use just lots of water.
Change the solution.
Change the solution.
That's solvent.
Solvent. You could change the solvent, alcohol, right, that kind of stuff. We really aren't doing that in this chapter because we're sticking with water as a solvent. Anything else?
Maybe add in like a catalyst that would help dissociate.
Yeah, catalyst maybe. Complex formation, right? That does it too. When I was a student in general chem, we were given a little research project. We had to research how to convert silver chloride into silver nitrate. And so one of the steps is you have to get silver chloride to dissolve. Now, I knew silver chloride's insoluble. The solubility rule said silver chloride's insoluble, right? And even in hot water, if I used hot boiling water, it's still not very soluble. It just sticks around. It really doesn't dissolve. So I had to come up with other methods. So one of the methods is to try to dissolve it in acid. That's common. And so you could try to dissolve this in acid, like nitric acid. But is there a driving force for this? So this is going to form silver nitrate and hydrochloric acid. Is there a driving force for this?
No.
No. No driving force for this. And so it didn't seem like I could use acid to dissolve this because, the leveling effect here, because all strong acids are the same strength. And so I gave up on this route because it didn't. And at this point, we hadn't talked about complexes. And so I was stumped. I couldn't figure out how to dissolve it. Silver chloride. I could try base, but, didn't seem to work. But one of the things I didn't realize is that, when you alter conditions, things change. And so, let's talk silver chloride is not soluble. It's not going to react with acid, right? Well, I should have been thinking, well, how can I make it more soluble? Or how can I get it to react with acid? Is there a way to get it to react with acid here? Could I get this to react with nitric acid?
Yes.
How?
Add HCl as well.
Add HCl as well? And adding HCl would do what? How could that help then? Adding HCl would seem to actually make it less soluble, because adding HCl would be common ion effect, and that would actually appear to make it less soluble. Well, that's it. When we do these types of predictions, like Chem 1A style predictions, what I started the semester with, we make certain assumptions. What were the assumptions that we made for making predictions for the three types of reactions we encounter?
That there's a driving force.
Okay, driving force. The driving forces we kind of figured out, precipitate, et cetera, et cetera.
We assume that in Chem 1A the reactions went to completion.
Yeah, we assume if there's a driving force, they go to completion. We also assume something else. What else did we assume regarding driving forces in Chem 1A? I know this has been a while ago because I talked about this in the first week of class. A long, long time ago.
The concentration is 1 molar?
Yeah, that's it. One of the things we assumed was that the concentration was 1 molar, so I was fixed. I was sure that this was not going to react, right? Because the driving force told me it's not going to react. But you know what? How could I get this reaction to become more favored? I should have been thinking at the time, Le Chatelier's principle, because what would Le Chatelier's principle say here? How could I get this reaction to favor the products more so than they currently do?
Add more reactants.
Yeah, add more reactants. And so I'd add more HNO3. Well, adding more HNO3 involves not just adding more, making the concentration higher. And so using Le Chatelier's principle, maybe if I make the concentration higher, I could push this equilibrium to to the right. That's something that never occurred to me, because I thought, oh, there's no driving force, there's no reaction. And so I immediately abandoned this method, but then I didn't think about, how could you change this? Well, changing these types of things with concentration and with temperatures in the next chapter, chapter 19, but we aren't going to get to chapter 19 just yet because we're going to go back and cover chapter 14 first, and then chapter 19. But it turned out the way that they wanted us to dissolve this is they wanted us to dissolve silver chloride in concentrated nitric acid. And not only concentrated, but hot concentrated nitric acid. So you just get boiling nitric acid, basically, and you dissolve your silver chloride in it. When you dissolve it, we all did this reaction in the lab. And you have to do it in the hood because it generates lots of brown fumes. So the brown fumes are NO being oxidized with oxygen and air to NO2. NO is a colorless gas, NO2 is a brown gas. And so if we're forming NO, that means that this is not a metathesis reaction. What type of reaction must it be? If we're forming NO, it's not a metathesis or double replacement. It is a redox. It turns out when you use hot concentrated nitric, you get some redox reaction when nitric acid oxidizes the chloride to chlorine, basically, and gets it to dissolve, and you have excess nitric acid, so you can form silver nitrate in the end, and some other stuff. So you have to isolate and purify it, basically. Using hot nitric acid was fun because you don't use that every day, and you don't generate these huge plumes of brown vapor all the time. You do it in the hood. It fills up the hood with brown fumes. But was there an easier way to dissolve the silver chloride than using hot concentrated nitric acid is dangerous stuff too, right?
So just keep increasing the concentration.
Well, I guess we could, but there's a limit, There's a maximum concentration that will hit. Oops, for nitric acid. So let's do an example. How did you guys dissolve silver chloride? Was it a huge ordeal to dissolve the silver chloride? No, it was really easy, wasn't it? What did you do? You just added ammonia. And so that would have been easy if I only knew at the time. I could have dissolved it with ammonia and then just killed the complex with nitric acid, and I have my silver nitrate. Pretty easy, straightforward procedure. But what I want you to do in Chem 1B is do this. Let's say I have silver chloride solid, 1 gram of this stuff. And you guys use 6 molar ammonia, right? And so the question is, how many drops of 6.0 molar NH3, how many drops are required to dissolve the AgCl completely? And so why don't you try this one and see, how many drops it would take to dissolve.